Okay. In this chapter, I will explain about the reasons for using attention mechanisms in LLMs, about the causal self-attention mechanism, and about stacking multiple attention modules into a single multi-head attention unit. To show the importance of using the self-attention mechanism in LLMs, let's discuss about the issues we are facing when we try to model line sequences with LLMs without using mechanism attention. So suppose we want to develop a language translation model, for example, from German to English, as shown in this figure. It's clear that when translating text from one language to another, it's not possible to merely translate word by word. Instead, the translation process requires contextual understanding and grammatical alignment. Please note that the word embedding process in LLMs is static, so it does not reflect how the meaning of the word changes in context. For instance, consider the text completion task. For this sentence in English, the chicken don't cross the road because it was two. Here, the word it may refer to chicken, or may refer to road. So we have two options for completing the sentence depending on whether the word it refers to chicken or to the road. If it refers to chicken, then we have the chicken did not cross the road because it was too tired. And for example, if it refers to road, then we have the chicken did not cross the road because it was too wide. As another reason for using attention mechanism, consider these two phrases with different meanings of apple, fresh apple, Apple iPhone. In first one, apple is a delicious fruit, while in second one, Apple is a mobile manufacturing company. To deal with this matter, the attention mechanism tries to build the contextual embedding of a word by selectively integrating information from all the neighboring words. So here the static embedding, and here we have dynamic contextual embeddings, two different vector for Apple, based on the contextual understanding of the self-attention mechanism. In fact, self-attention is a mechanism in transformers used to compute more efficient input representations by allowing each position in a sequence to interact with and weigh the importance of all other positions within the same sequence. In this chapter, we will explain this self-attention mechanism from the ground up before we explain the remaining parts of the GPT-like LLM in the following chapter. This figure depicts different attention mechanisms we will explain in this chapter. Here we start with a simplified version of the self-attention mechanism to introduce the fundamental concepts behind using attention mechanisms in LLMs. Then, in second step, we will explain the actual self-attention mechanism used in the GPT models and most other popular LLMs. This type of self-attention mechanism uses trainable weights to calculate the contextual embeddings. In third step, we will introduce the casual attention mechanism by adding a mask to self-attention. This allows the LLM to generate one word at a time by considering only previous and current tokens in an input sequence. And finally, we will see the multi-head attention that organizes the attention mechanism into multiple heads, allowing the model to capture various aspects of the input data in parallel. Okay, so here we start with developing a simplified version of the self-attention mechanism to understand the basic concepts. The goal of self-attention is to compute a context vector for each input element that combines information from all other input elements. In this example, we compute a context vector Z2 that's related to second token X2. The importance or contribution of each input element for computing Z2 is determined by the attention weights alpha to 1 to alpha to t. When computing Z2, the attention weights are calculated with respect to input elements x1, x2 until xt on other inputs. Here is the flowchart of computing the attention weights and context vectors from input vectors in self-attention mechanism. Okay, in step 1, we compute the attention scores as dot products between input. Then, in step 2, we normalize the attention scores to obtain attention weights. And finally, in third step, the context vectors are computed as weighted sum over the inputs. As an example, consider this input sentence with 6 words. Your journey starts with 1 step, where the embedded tokens are shown here as a vector of 3 elements. The overall goal is to illustrate the computation of the context vector Z2 using the second input element X2 in all other input elements as a dot product. Note that in this figure, to reduce visual clutter, the numbers are truncated to 1 digit after the decimal point. As you can see here, the attention scores omega 21 until omega 2t are computed as the dot product between query token x2 with another inputs x1, x2 until xt. So these are attention scores. After computing the attention scores, omega 21 to omega 26, with respect to the input query x2, the next step is to obtain the attention weights alpha 21 to alpha 26 by normalizing the attention scores. This normalizing process is shown here in this figure. Normalization of the attention scores. After calculating and normalizing the attention scores to obtain the attention weights for query x2, the final step is to compute the context vector z2. This context vector is a combination of all input vectors x1 to x6 weighted by the attention weights alpha 21 until alpha 26. So far, we have computed attention weights and the context vector for input x2. In this figure, you can see the result of computations to calculate attention weights for all 6 inputs. The highlighted row, second row, shows the attention weights for the second input element as a query. Please note that the numbers in this figure are truncated to 2 digits after the decimal point. Actually, the sum of values in each row should be 1. The sum of values in each row should be 1. What we explained so far was a simplified version of the self-attention mechanism. In this section, we developed the actual self-attention mechanism used in the original transformer architecture in 2017 and in the GPT models and in most other popular LLMs. This type of attention mechanism is based on a set of trainable weights. In the first step of the self-attention mechanism with trainable weights, we compute parameters named query Q, key K, and value V vectors for input elements X. Okay. Similar to previous section, we consider the second input x2 as an example. Here, the query vector q2 is obtained via matrix multiplication between the input x2 and the weight matrix wq. Similarly, we obtain the key and value vectors K2, V2 for input X2 and all other input elements via matrix multiplications involving the weight matrices WK and WV. Here, the attention score is obtained by a dot product computation similar to what we use in the simplified attention mechanism before. The new aspect here is that we are not directly computing the dot product between the input elements, but using the query and key obtained via the respective weight matrices. Okay. After computing the attention scores, omega, the next step is to normalize these scores using the softmax function to obtain the attention weights alpha, alpha 2, 1 until alpha 2, 6. Okay, now the main question may be, what's the softmax function? We will explain about softmax in later slides soon. In the final step of the self-attention computation, we compute the context vector by combining all value vectors via the attention weights. Here we computed the context vector Z2 again by combining all value vectors via the attention weights. Okay, now let me to explain about softmax function. Softmax is a generalization of the sigmoid function, a popular activation function for neural network architectures. Here the sigmoid function 1 over 1 plus e minus z. The sigmoid maps the output into the close range between 0 and 1, which is useful in squashing outliers towards 0 and 1. Here is the softmax function. For the k-dimensional vector z. For better understanding, see the numerical example shown at the below of this slide. Here. Z, softmax Z. Okay, a summary for this section. Consider this figure that shows the whole process in a matrix form. First, we transform the input vectors in the input matrix X with the three weight matrices WQ, WK, and WV. The result will be queries Q, keys K, values V. Then we compute the attention weight matrix based on the resulting queries Q and K. Finally, by using the attention weights and values V, we compute the context vector Z. Okay? This is the summary of this section. Here is what we've done so far. We began with a simplified attention mechanism. Then we added trainable weights to reach the actual self-attention used usually in LLMs. In this section, we are going to extend the casual attention mechanism by using the casual and dropout masks. Later, in next section, we will discuss about stacking multiple attention blocks into a single multi-head attention unit, which will be used in practical LLMs. Okay. In a casual attention, we mask out the attention weights above the diagonal such that for a given input, the LLM cannot access future tokens when computing the context vectors using the attention weights. For example, for the word journey in the second row, we only keep the attention weights for the word your, that's before, and the word journey, that's in the current position. An efficient way to obtain the masked attention weight matrix in casual attention is putting minus infinity to cells in upper triangle. In practice, the softmax will turn it to 0. Okay? In casual attention mechanism, not only we use the casual attention mask here, upper left, we also apply an additional dropout mask here, upper right, to zero out additional attention weights in order to reduce overfitting during training. So the combined mask is here, the combination of dropout mask and attention mask. Now we consider the multi-head attention mechanism, that's a collection of multiple casual attention mechanisms. As an example, consider this figure in which the multi-head attention module includes two single-head attention modules stacked on top of each other. So instead of using a single matrix WV for computing the value matrices, in a multi-head attention module with two heads, we now have two value weight matrices, WV1 and WV2. Similarly, for other weight matrices, we have two, WQ1, WQ2, WK1, WK2. Okay. In this way, we obtain two sets of context vectors, Z1, Z2, that we can combine into a single context vector matrix Z. Okay, in next chapter, we will learn about LLM architecture. That chapter explains about the structure of the transformer blocks and different layers in LLMs, including the normalizing layers and shortcut connections to stabilize neural network training. If you have not done so yet, please join our community by hitting the subscribe and notification bell icons. Thank you for your attention.